In this video, we're going to talk about an example as well as the idea of what's called a rejection region and talk a little bit more about type 1 and type 2 error. You work for a paperclip factory that makes and distributes paper clips. The east wing of the factory makes 1-inch paper clips. Every week, you take a simple random sample of 1,000 paper clips to make sure the machine is working properly. You estimate that 1% of all paper clips have to be thrown away because they are defective. This week, your sample finds 21 defective paper clips. Is there evidence that the machine is not working as claimed? And I said I'm going to perform this as a two-sided test. So, to begin, state the null is that the proportion is 0.01. The alternative is that it is not 0.01. And remember, we must define our parameter. P is the proportion of defective paper clips. Our plan. Well, it is a proportion, so we had a simple random sample. The next condition is that our sample size is less than or equal to 1/10 all paper clips. And last, that our sample size multiplied by our proportion and our sample size multiplied by the complement, well, this is 10. This is 990. Remember, it had to be greater than or equal to 10. So we're good. The do. We're going to do a I should say up here, we're doing a 1 proportion Z test. We should put that in the plan. Okay. So we go to the calculator. So I have gone into the calculator. You can see the 1 proportion Z test. Proportion from the null. Our sample, 21 out of 1,000, not equal to. I did draw, so you can see the Z statistic and the p-value. Remember, what you actually need to report here is the what we call test statistic and the p-value. Okay? So, conclude. Well, we reject the null, and remember, we must say why. And of course, it's in this case that our p-value, and you could write it as a number, you could write p-value, is less than, and I did not provide you with a significance level. Of course, most industries use 0.05 or 0.01. So we say what we did and why, and then we put some context to this. We have evidence that the proportion of defective clips is not 0.01. All right? So sorry my writing's a little sloppy there, but just make sure you're seeing all these things and some of the nitty-gritty stuff you have to do. Okay? The null and alternative always seems obvious, but make sure you define the parameter. Say what test, use the correct conditions, use the test statistic and p-value in your conclusion, say what you're doing and why in relation to the p-value, and then put that in context. A quick couple words here about two-sided tests. A lot of times a two-sided test, like we did in the opener, is actually more based on like a preliminary rejection region idea. And here's what I mean by that. If let's say the paperclip company had a statistician out and they said, we understand, it's a mechanical process, there's going to be some defects. They might say, I understand that the proportion will be around 0.01. The statistician would say, I'm going to set a rejection region for you. That if you take your sample of 1,000 paper clips and go like 0.02, that might even be too much. Or, I guess 0, or maybe 0.015 or something like that. that take your weekly thing, and if it comes out to be 20 clips, that's too big. If it comes out to be, one clip. So you might send this like preliminary rejection region as to, saying, like leaving it in the hands of someone else to check. But you're telling them the machine's not working properly if the proportion is this or beyond. Okay? The clues on the AP exam, of course, are reading the words, is it, is not, or is different, is not what we said it was, is different than it used to be. That means we're using a not equal to. If you're asked to test at the 0.05 level, you build a 95% confidence interval. If you're asked to test at the 0.01 level, that means we're testing at the 99% confidence level. Often, this is a little confusing because 95, of course, would cut off 2.5 on either side. And, of course, in a one-sided, we do 0.05. Really, it comes down to the fact that 0.05 level, in terms of a two-sided test, means we want to capture 95% of sample proportions or means, or in this case, 99. Okay? So again, most of the time in real life, a two-sided test is almost done before any sampling is gathered, and you just want an idea of like what range is going to cause me to say this process is working correctly. We've already talked about errors a little bit. That type 1 error is reject the null when the null is true, and that type 2 is fail to reject the null when the alternative is true. This, if you remember, type 1 error is always the significance level. And the idea here is that, if we think about our distribution of values and we say, well, 5%, we put the significance level there and there's 5% left outside, 0.05, these samples are improbable but possible. And if our rejection region is everything over here, then 5% of the time we're going to reject possible but improbable outcomes. And that's why that we reject the null, but in fact the null was true. Anything that is inside the null tail means that the null could have been true, but it would have been rejected. That's type 1 error. It's whatever the significance level is. The type 2 error is a little bit harder to think about. It's when we don't reject the null, but in fact the alternative is true. And I'm going to show you some pictures of this in a moment, but very simply, if I think about two curves, I'm going to draw two. I'm going to call one the null curve. Here's the null. And I'm going to call the other the alternative curve. Here's the alternative. So if I have a significance level like this, right? The stuff that is right here in the tail of the alternative, this would cause me to fail to reject because it's inside, it's on to the left of the kind of black cutoff, this significance level, and yet it's inside the alternative's curve. So this is type 2 error. The power of a test is the complement of that. Of course, we want our power to be high because that signifies that our type 2 error was small. So think about it this way. Power is the probability that the test will reject the null when the alternative is true. And we want a high power. We want, if the alternative is true, we want to reject the null. We don't want to commit type 2 error that we don't reject and the alternative is true. Let me show you just some animation of this and then we'll kind of come back to this idea. So here's what I was referring to, this curve. And this on the left, this is the null and this is the alternative. Okay, you can see I set the significance level at 0.05, so it's just cutting off 5%. That's my type 1 error. And the type 2 error is the part of the alternative distribution that is causing us to not reject the alternative. So it's this right here. So there are a lot of things we can do to cut down our area of blue. One thing we can do is slide the curve this way. But that's kind of weird because what that means is we just changed the mean of our alternative. So that's a little bit unrealistic. We don't have control over that. Another thing we could do is we could change the deviation. Look at this. That would make it fatter if it's a bigger deviation. So if it were skinnier, look, there's no type 2 error now, right? They're not The tail is not going into the other curve. But again, we don't have the power to do that. We could change the significance level. We could do that. That changes type 2 error, right? But of course, to minimize our type 2 error, we'd actually need to move the significance level bigger. So many times we don't change the significance level because that would require us to change type 1 error. So the one thing we can control is sample size. Larger sample leads to less variability and therefore will decrease type 2 error. So again, to just kind of run through, remember this is the null, this is the alternative. We can slide them apart to get rid of this tail. Okay, slide in, you can see out the blue. We could change the deviation, change the significance level, or we could change sample size. But only one of those things do we truly control. Okay, so let me just run through the 4 things we just talked about. We had 4 ways to increase the power or decrease type 2 error. We could change the significance level. We use this alpha for that. Okay, we could change the deviation. We could change the center of our alternative curve, or we could increase the sample size. There are only 2 of those things, 1 and 4, that we can control. And the problem with changing the significance level is it increases our type 1 error. So to get rid of type 2, we increase type 1. So the only way, the best way to increase the power is to increase the sample size. On the AP exam, this is almost the only thing that is ever asked about type 2 error and power.